so that you may connect to your session if you're here for Math 1324. Without further ado, I'll pass it on to our presenter so that we may begin.
Good morning and thank you so much. And everyone, welcome again to our Friday Math Happy Hour. It's our Friday before our spring break. I'm sure all of you are in desperate need of a little break. But anyway, let's go ahead and get to it. For today's Friday Happy Math Hour, if you're here for the 1314, it's going to be covering finding zeros of polynomial functions. And again, if you are here for the Happy Math Hour for the Math 1324, you will find the link in the chat. So without further ado, let's go ahead and get started. Okay, so finding zeros of polynomial functions. So what I'm going to go over is section 2.5 from your book. Okay, so a quick little review. Finding zeros of a polynomial function, okay, what that means is we want to find where the graphs of these polynomial functions cross the x-axis. In other words, the zeros of a polynomial are the x-intercepts, okay? So if we look at these graphs here, if we look at this first one here, okay, um, we have zeros at -1, at 2, and at 4. These actually, zeros actually cross the x-axis, right? But if you look at the graph 2 here, we covered last week, when a graph touches the x-axis and turns around, okay, this is still considered a zero, but we call this a double zero, right? This is a multiplicity of 2, okay? So, and it's here on the solutions, we have a -2 and a -2 twice. That's because the graph touched and turned around on the x-axis. But here at 2, 0, the graph completely intersected the x-axis, so we only have 1, 0. Yes, so we have a odd multiplicity or just a multiplicity of 1. Okay, so then again on this third graph example, again we covered this last week. This particular polynomial is a degree 4, so it's going to have 4 zeros or 4 solutions. Okay, again, the one here at the origin, 0, 0, we call this an even multiplicity because we have 2 zeros. Okay, and again, the zeros of a polynomial function are where the graphs cross the x-axis, or in other words, the x-intercepts. So to help us finding these zeros, let's review this theorem here. And this is the fundamental theorem of algebra. And the fundamental theorem of algebra says that if we have a polynomial degree n, meaning anything higher than 1 or larger than 0, we're going to have at least 1 0 in the system. And also we may have a complex number in the system. So an nth degree polynomial has exactly n zeros. Okay. And to better understand this, let's look at some examples here. So this first one says, determine the number of zeros of the polynomial function. So all they're asking us to do is how many possible zeros will these polynomials have? So if I look at this first one, I just have to look at the degree of the polynomial. The degree of this polynomial is of degree 3. So this polynomial will have at most 3 zeros. Okay. And I say at most because it could have 3, it could have 2, or it could have 1. Now, depending on the polynomial, it may have, since this is an odd polynomial, it's going to have at least 1, okay, but at most 3. If we look at the second one, okay, we have the degree of this polynomial is 6, okay, so then this polynomial will have at least 6 zeros, okay, and I say at least 6 because it could have 6, it could have 5, 4, 3, 2, 1, or none. Okay, since this is an even polynomial, okay, we can have none. It may not cross the x-axis at all. Okay, so now that we can determine how many polynomials, how many zeros a polynomial can have, let's find the zeros of a polynomial. So for instance, the first example, hopefully it's easy. It's find the zeros for this function x minus 2. So to do that, again, what we want to do is we want to find out where it crosses the x-axis. And just to review chapter 1, okay, to find the x-intercepts of a function, we just set y equal to 0, which is what I did here. Okay, so, and then I solve for x. To solve for x, I added 2 on both sides, and it gave me x equals 2. And again, this is a linear function or a linear graph, and it shows me where it crosses the x-axis, and it crosses the x-axis here at 2, 0. Okay. Um, this one we've dealt with already also. This was from 2.1 and also from chapter 1. We have a quadratic, okay? There's several ways of graphing this quadratic, but again, if we would use our quadratic formula to find our x-intercepts, we would find that this graph has a x-intercept at 3, okay? Now, again, we at most this graph is going to have 2 intercepts, and it does, right? We say that here at 3, since the graph crossed, I'm sorry, um, since the graph here crossed, just touched the x-axis, again, this 3 is a double zero, so it's 2 threes, yes? So again, this graph has two zeros, and it's at 3, yes? And again, you can see it here. When I factor this out, you're able to see that I have 3 twice. It's a double zero, yes? Now, x equals 3, x equals 3. All right, now if we look at this third example, f of x is equal to x times x minus 2y times x plus 2y. Okay, again, we covered complex numbers last week, and this is what we're talking about, that a polynomial function can have um, a complex number, okay, a solution. So in this case, we can see that if x is equal to 0, we have 1, 0 here. Here, if we don't see it, we can set up the equations, right? When will x be 0 when we have a minus 2i? So if we add 2i on both sides, we can see that we have a complex 0 here at x equals 2i. And same with this one. We have a complex number here at x equals minus 2i. So again, if I were to multiply this polynomial together, I'm going to have a degree 3 polynomial. Hence, I'm going to have 3 zeros. One of them is a real 0. The other 2 are complex 0. And you can see it on the graph. This graph only crosses the x-axis one time, which is at the 0. But again, because it's a degree 3, it's going to have also the remaining 2 zeros that does not cross the x-axis are those imaginary, or they come from the complex numbers. Okay. All right, so let's look at this one. Find the zeros of the polynomial given that the x is equal to 4 is a 0. So on this particular problem, they're helping us find the remaining zeros. So again, at most, how many zeros will this polynomial have? So this polynomial should have at most 3 zeros. Now it will have 3 zeros, and it might be, some of those might be complex. So they're helping us out that they are giving us one of them is already, they're giving us one of the zeros, which is 4. So in order to help us solve this, okay, we can use synthetic division, something that we learned last week, in order to make this polynomial 1 degree less. And we saw that when we use synthetic division, this is my dividend, and when I divide it, my quotient is going to be a degree less. I'm going to end up with a quadratic. Now, why do I want to do synthetic division, or why do I want to divide it to have 1 degree less? Is because in this format, it would be very difficult for me to factor. But if it's in a quadratic state, I have a lot of tools under my belt that will help me solve for that quadratic. Again, we have the quadratic formula that will always work, but we can always factor, or we can use a square root property. Okay, so let's also review synthetic division, because again, you might see it on a test coming up. So here, since they tell me that is x equals 4 is a 0, I'm going to use 4 to divide. And the reason why I'm going to use 4 to divide is because when I divide this, I know that my remainder is going to be 0. And hence, my quotient is going to be left as a quadratic. Okay, so again, to review synthetic division, we're only going to get the coefficients of the polynomial of our dividend. So here it's a degree 3. We gotta make sure that it's in order and all placement values are accounted for. So this is a degree 3. Oh, but we're missing the square. So again, we're gonna use 0 for the square. We have the negative 13 for the x, and we have the negative 12 for our constant. So again, it was in order. The only thing that was missing was my square value, which I am representing as 0. So let's go ahead and do this. This first step is I bring down my 1, and then I multiply 4 times 1 is 4. Then I add 0 plus 4, which is 4. Then I multiply again. 4 times 4 is 16. Negative 13 plus 16 is a positive 3. 4 times 3 is 12. And negative 12 plus 12 is 0. Now, I knew my remainder was going to be 0, okay? Because they told me that this was a 0 of this polynomial. But again, the reason why I did this is because now I can look at my quotient. And if I rewrite my quotient, this one is x squared. The coefficient is 1. This is the coefficient of the x, which is 4x. And this is my constant, 3. And if you see here, I am going to factor it out. So x squared plus 4x plus 3 factors out in this format, x plus 3 times x plus 1. So the product of any two numbers that will equal to 0 is that any of these two could be 0. So if you don't see it, you can solve it algebraically. But hopefully we can see that if I would put negative 3 for x here, negative 3 plus 3 will give me 0, and 0 times anything, the answer will be 0. Here, if negative 1 is x, negative 1 plus 1 is 0, and 0 times anything will give me a product of 0. So hence, the zeros are the ones that I found were negative 3 and negative 1. They gave me the x equals 4. So please be mindful when you're putting these answers on your homework, okay? Don't forget to put the 4 that they gave you, okay? Don't just put negative 3 and negative 1. You also have to put in that x equals 4, the one that they gave you, okay? All right, so let's look at this one. Find the zeros of the polynomial function. Now, in this example, compared to the previous example, um, they had given me one of the zeros. So they're not doing that in this case. So to help us with that, what we can do is we can guess what a zero could be for this polynomial, but that could be infinite possibilities, and we can take a long time to find a zero for this polynomial. So there is a shorter way to uh, get a shorter list or a smaller list to find a possible zero for this polynomial. Again, I don't want to try infinite number of solutions. So in order to help me with this, what I'm going to do is something called the rational zero test. And the rational zero test, again, just like the name sounds, is just a test to possibly find a zero of a polynomial. And again, it's a test. Just like any test, I can get a positive solution or I can get a negative solution, right? I always like to joke back in the pandemic year, we always wanted our test to be a negative, right? We never wanted to be positive. But again, in this case, we want something positive. We want to try to find a true zero. And again, this rational zero test is going to minimize our infinite number of possibilities to just a few. And the way you do the rational zero test is this. You get the factor of the constant term of the polynomial, and you just get the value, okay? You don't have to get the sign, and I'll show you why, okay? And we're going to divide it by the factor of the leading coefficient of that polynomial. Okay, so for instance, just to review, okay, we color coded them. The factor of the constant term is the one with no x value. This is the last term, the a0, so it's the green one. And the leading coefficient, if you guys remember, is the coefficient that is associated with the degree of the polynomial. So the one with the highest exponent is the leading coefficient is the coefficient that's in front of that leading degree. Yes? So let me give you an example. What is a factor? Okay. So for instance, if I have the number 8, the factors to find the numbers of 8 are 1 times 8 will give me 8, and 2 times 4 will give me 8. So the factors of 8 would be 1, 2, 4, and 8. How about 24? What are the factors of 24? Or what are the makeups of 24? So to get 24, it's 1 times 24, 2 times 12, 3 times 8, 4 times 6. So the factors of 24 would be 1, 2, 3, 4, 6, 8, 12, and 24. These are the factors of 24. Okay, so going back to my question here, let's use the rational zero test to find the possible zeros that this polynomial will have. Okay, so again, what I will do first is I'm going to get the factors of the constant term. My constant term here is 9. Now, I know it's a negative 9, but again, all I'm interested is in its value, and I'm going to show you why in a second. I keep telling you this, but I will show you. Okay, and then I'll say, what is the leading coefficient factor? So again, my leading coefficient here is 1. So my only factor for 1 is 1. Again, my factors for 9 were only 1, 3, and 9. Now, the reason why I'm not interested in the sign of either the leading coefficient or the constant term is because I'm going to be looking at all aspects of that value. I'm going to be looking at the positive and negative. Now, unfortunately, WebAssign doesn't have this symbol, the plus or minus symbol. So when you do the list or listing these on your homework, you got to list them all -1 plus 1, -3 plus 3, -9 plus 9. Okay, so that would be the answer. You're going to have a hopefully probably a test question that says, what are the possible zeros that this polynomial have? Okay, and this would be the answer. You would use a rational zero test to answer that question. Okay, so let's go ahead and use these. So now if you see here, instead of having infinite number of possibilities to choose from, now I only have 6 to choose from my list. Okay, now again, how many zeros will this polynomial have? Well, this polynomial will have at least 3 zeros. Yes, so again, they gave me 6. Now this is a test. These 6, maybe 3 of them are in there, maybe 2 of them, or maybe one of them, or maybe none of them are in there. It's just a test. Yes, so rule of thumb when using the rational zero test, always start with the first one. I'm going to start with +1, and I'm going to use synthetic division, which allows me to help me um, find out if this is a true zero or not, just like my first example that I did. Okay, so let's go ahead and do this. I want the remainder of 0. If I get a remainder of 0, x equals 1 is a 0 or solution of this polynomial. So let's get to it. So again, we bring down my 1. 1 times 1 is 1. 1 plus 1 is 2. Let's multiply again. 1 times 2 is 2. Minus 9 plus 2 is -7. Multiplied by 1. 1 times -7 is -7. -9 minus -7 is a -16. This is my remainder. It says my remainder is not 0. 1 is not a 0, this polynomial. So, again, and it makes us sad. So let's go ahead and try it again. What I'm going to do now is going to try the next number, the -1. Okay, so again, I'm going to do synthetic division again. I'm going to multiply my value. So again, to review, I'll bring down my 1. -1 times 1 is -1. 1 minus 1 is 0. -1 times 0 is 0. -9 plus 0 is -9. -1 times a -9 is a +9. And -9 plus 9 is 0. Awesome. This is what we wanted. We wanted a remainder of 0. So what this is telling me is that at x equals -1 is a 0. So now I can do the same thing like that previous example. Have one of the zeros, I have 2 more to solve. So what I'm going to use is my quotient from this division to find the other remaining zeros. Because, again, now I'm dealing with a quadratic. Again, I started with a cubic function. Again, division will lessen or give me 1 degree less. So now this 1 is associated to 1 times the x squared. I don't have an x value, but -9 is my constant term. So now I can use my square root property to solve for this one. Okay, so what I'm going to do is I'm going to add 9 on both sides. Okay, take the square root of both sides, and the square root of 9 is going to be plus or minus 3. And now I have the solution for this graph. The zeros for this polynomial are at x equals -1, which is the one that I found from synthetic division, and at x equals -3, and at x equals 3 using my square root property. Yes? Now, these are my zeros. sometimes you're going to be asked to find the factors of the zeros. Okay, so to find the factors of the zeros, it's very easy. You just have to move that one back to the x. So I'm going to add one back to the other side. So the factors of this polynomial are x plus 1, x plus 3, x minus 3. Okay, so there will be homework problems or possibly a test question that will say, answer this polynomial with its factors. Okay, and this is how you do it. All right, let's try it one more time. It says, find the rational zeros of the polynomial function and enter as a comma separated list. If the answer does not exist, answer D and E does not exist. Okay, so again, I'm going to use the rational zeros. Uh, I'm going to use the rational zero test, excuse me, to find the possible zeros. So first, my constant term is 1. Okay, again, I don't care that it's a negative. Again, I'm going to be looking at all aspects of it, so I'm only interested in the value. Then the leading coefficient, the one in red, is 2, so the factors of 2 are 1 and 2. So again, the rational zero test is the constant divided the constant factors divided by the leading coefficient factors. Again, so the list would be, again, and I do apologize, again, your website does not have plus or minus symbol. And on website, you're going to have to put minus 1, comma, plus 1, comma, plus 1 half, comma, negative 1 half. Okay, that's how you would put them. Okay, all right. So now that I have the possible zeros, if you see here, if I go back, instead of having infinite number of possibilities, the rational zero test brought down my possibilities to just 4, which is a lot better to test than a whole bunch, right? So now again, I'm going to start with the first one, and again, I'm going to use synthetic division. Again, we got to be mindful. I have a degree 3 polynomial. Is it in order? Do I have a placement value for all? I have a 3, 2. We're missing the x. So again, for the x, I'm going to plug in 0. Negative 1 is my constant. Let's go ahead and do synthetic division. Okay, so again, bring down my 2. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. 0 plus 5 is 5. 1 times 5 is 5. Minus 1 plus 5 is 4. Since the remainder was not 0, x equals 1 is not a 0. So let's go ahead and use the very next one. Let's try it one more time. Okay, so negative 1 times 2 is negative 2. 3 minus 2 is 1. Negative 1 times minus 1 is negative 1. 0 minus 1 is 1. Negative 1 times a negative 1 is a positive 1. And negative 1 plus 1 is 0. Awesome. So again, what this is telling me is that x at equals negative 1 is a 0. So now again, I'm going to use my quotient, which is now a quadratic. Again, this is 2x squared, 1x, and the negative 1 is my constant. Yes? So now what I'm going to do is I can use any method to solve for the remaining two zeros. Again, this is a cubic function. It should have at least 3 zeros. I already found one. This one should have 2 more. Okay? So let's go ahead and factor once again. Again, that's my weapon of choice. I always love to factor. And again, as Ms. Chuka also mentioned last week, if you can't factor within the first 1 or 2 minutes, then stop. Just go to the quadratic equation, which is your best option because that's the the method that will always give you the solution. Yes. So again, this one factors by 2x minus 1 times x plus 1. Again, I use my zero property that says that for this to be equal to 0 when I'm multiplying two numbers, either this is 0 or this is 0, right? So all I have to do now is solve for x on both. So add 1 on both sides, divide by 2 on both sides for this first one. So one of the zeros is at x equals 1 half, or my second 0, excuse me. And this one, hopefully it's easy to see, that if I put negative 1 for x, negative 1 plus 1 will give me 0. And voila, I have all three zeros. Again, please don't forget the one that we just found by using synthetic division. My zeros are at negative 1, 1 half, and negative 1. Okay, so again, just to review, um, if I this -1 appears twice, so this has a multiplicity of 2. So -1 has an even multiplicity. And what does it also mean? That at -1, my graph just touched and then turned around at this point. Okay, all things to remember when graphing for your coming up homework or exam. Okay? All right, let's look at this example. Find the rational zeros of the polynomial function. Enter answers as a comma separated list. If answers do not exist, again, we're going to enter D and E. So again, let's look at this polynomial. What is the degree of this polynomial? The degree of this polynomial is 6. So this function, even though there's only two terms here, this should have at least 6 zeros. Yes? So let's go ahead and do it. So the first thing that I would do to try to find the zeros is there's several ways to solving this. So one of the ways that I am going to do is first um, kind of the long way, okay? So what I'm going to do is I'm going to use my rational zero test to find the possible zeros. So here, again, I don't have a constant term. There's nothing with not an exponent, so that's 0. And then my leading coefficient is 1, so that's plus or minus 1. So again, this tells me that possible 0 is at 0. Okay, so and this is true, right? If I were to put to 0 here, 0 squared is 0, 0 to the 6 is 0, 0 minus 0 is 0. So yes, this helped me and it helped me solve for one of them, but that's only one. I'm still missing 5, right? So let's use synthetic division. And knowing that I have a 0 here, let's go ahead and plug it in. Again, I have a degree 6, so let's see. The 6, the leading coefficient for the 6 is a -1. I don't have a 5, so that's a 0. I don't have a 4, so that's a 0. I don't have a 3, so that's a 0. Oh, I have a square, and the coefficient for the square is 1. Okay, I don't have a t by itself, so that's 0, and I don't have a constant, so that is 0. Okay, so let's go ahead and do synthetic division. Okay, if you see here, okay, I'm going to bring the -1 is 0 times -1 is 0, and this is going to produce zeros all the way through. Yes, but what I see here is that my quotient from this one synthetic division, I brought it down to 1 degree. Now it's t to the 5th power. It's of degree 5th. Guess what? I can use synthetic division once again to keep on minimizing that degree. Okay, so what I'll do is I'm going to do synthetic division again, and I'm going to use 0 again. And again, when you see that I do synthetic division again, I'm going to have a 0 for the remainder. So again, my quotient is now -t to the 4th plus 1. Oh, I just lowered it one more time. So guess what? Let's keep on doing it until we can simplify it. Or actually, I could stop here, but I think we can try it. No, let's stop here. And this is my option would have done. I would have stopped here because here I can see that this guy here, we can simplify this, right? We can subtract 1, take the square root of both sides, and we can see that this term here can factor in these two terms. Minus t squared minus 1 times t squared minus 1. Again, use my 0 property to solve, okay? And on this particular one, again, I'm going to subtract 1 on both sides. Um, Divide by a -1 on both sides. And when I take a square root of the -1, again, we've covered this already. This is a complex number, the square root of -1. The answer is imaginary. So we're going to have a plus or minus I for this solution. Now, if I do this one, t squared, I'm going to add 1 on both sides, take the square root of both sides. This one does give me just t is equal to plus or minus 1. Okay, so if I do my list here, okay, and plug these in, if you see here, I have 1, 2, 3, 4, 5, 6 zeros. 4 of them, which are true zeros or real zeros, where they're actually crossing the x-axis. Again, you see here at 0, I have 2 of them. This is my even multiplicity. The graph just touches and turns around. Okay, and how do I know that this graph looks like this? Again, from stuff that we covered. This is an even function. So if I look at my end behavior for an even function, when the leading coefficient is negative, the graph is going to be falling from the left and falling from the right. Okay, so if you see, everything that we cover keeps on building, so we can do more and more stuff with this information. Okay, so again, hopefully this example helps. All right, so again, these are my zeros. So the second way that I could have done it was just by factoring right from the get-go. I saw that I have a t squared minus t to the sixth. So the smallest power that these both share is the t squared. So I would factor that out. So t squared times 1 minus t to the fourth is equal to 4. And you see here, now I use my zero property and I'm have the same problem that I had before, using it the long way, just using the synthetic division. Again, always look for factoring methods that you can use to simplify your work. Okay. All right. So let's look at this long one. Okay. This one looks scary, but if we follow the same steps, this should be no problem to solve. Let's find the zeros for this polynomial. So again, let's look at the degree of this polynomial. This is the degree 4. So this polynomial should have at least 4 zeros. Okay. So let's go ahead and use our rational zero test to minimize the possible list of choices that we want to use. So again, my constant term for this one is 24. So the factors of 24, which was my example that I showed you before on the factors of 24, are 1, 2, 3, 4, 6, 8, 12, and 24. Again, my factors for the leading coefficient, which is 9, are 1, 3, and 9. Okay, so again, I am going to do these. I'm going to do the positive and negative 1, positive negative 2, and so on and so forth for the constant term and for the leading coefficient. So if we look at this one, okay, this one is going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 times 3. Like, this is possibly 27 zeros, okay? But again, don't be intimidated. This only should have 4 zeros, and we just start from the beginning, okay? We'll start with the first one, okay? So again, if I were to write them out, again, unfortunately, you can't do this on your web assign. You're actually gonna have to do +1, -1, +2, -2, all 27 times. Yes, so I do apologize for that. Maybe WebAssign can create this plus or minus symbol one of these days. All right, so let's start again. Let's start with 1. Okay, so if using synthetic division, I see that 1 will give me a remainder, so hence 1 is not a solution of this graph. Okay, so then just to make my life simple, I just jumped from the -1 to the -2. Okay, and the reason why I did that is because I knew that at -2 was going to give me a 0. Okay, so if I see here, well, after doing synthetic division, and let me just review, okay, the synthetic division, I brought down the 9. -2 times 9 is -18. -9 plus a -18 is a -27. -2 times a -27 gives me the positive 54. -58 plus 54 is -4. -2 times a -4 is a positive 8. 4 plus 8 is 12, and -2 times 12 is a -24, and 24 minus 24 gives me my 0. Yes? Okay, so I hope all of you guys are experts in synthetic division, okay? I hope. Um, so here we see that I have a 0 at x equals -2, okay? And I'll have my quotient. Now again, my quotient is still not something that I can work with because I have a cubic, okay? Now, um, but if I look at this cubic is factorable, and I can factor by grouping, but let me see here. What I will do is I'll go back and show you the quick way, but again, first, let me just do it kind of the long way. If you didn't see the factoring, I'm just gonna process my process again for synthetic division. Okay, now I'm just gonna use the next following possibility, the +3. And again, if I use +3, oh, I end up that also 3 is a 0 of this polynomial. And guess what? Now my quotient is going to be a quadratic. Now I have 9x squared minus 4. Again, I can use my square root property to solve for x. So set this equal to 0, add 4 on both sides, divide by 9 on both sides, take the square root of both sides, and I end up that x is equal to plus or minus 2/3. Okay, so now I have all three zeros. Yes, so here all together, we'll put them together. We had that first one that we found when x is equal to -2. We found that x is equal to 3. I'm sorry, it was 4 zeros. And then we have the plus or minus 2/3. So we have, these are my 4 zeros. Again, if the homework had asked me for the factors, again, you just move the 2 to the other side. So the factors are x plus 2, x minus 3, x minus 2/3, and x plus 2/3. Okay. All right. So again, just to review and to recap, okay, um, the first problem on this problem says list the possible zeros of f. Again, what they're asking me to do is to use my rational zero test to find the possible zeros. Again, so the constant of this term is 9. So the factors of 9 are plus or minus 1, plus or minus 3, plus or minus 9. Get the factors of the leading coefficient. The leading coefficient is 1. So if I divide by these, nothing happens. So this is my answer. Again, you would answer plus 1, comma, minus 1, comma, plus 3, comma, minus 3, comma, plus 9, comma, minus 9, comma. Okay? All right. Then B says list all the real zeros. So let's go ahead and do that. Let's use synthetic division to bring this cubic into a possible quadratic. And if you see that if I used 1, the first one right off the bat, 1 is a solution. So again, this is my quotient. Okay, I have the x squared minus 9. Again, this gives me plus or minus 3 as the remaining zeros. So the zeros are at x equals -1, x equals -3, x equals 3. To represent this as factors, this is x plus 1, x plus 3, x minus 3. Okay. Now, I keep repeating this because you do have some homework problems that ask you to convert this polynomial into a product of its factors. So the answer would just be x plus 1 or parentheses x plus 1 times x plus 3 times x minus 3. Okay. All right. So little hints for you. Okay. So again, the list of the real zeros, again, as a list are just -3, -1, and 3. So with this information and with some prior knowledge, we can sketch the graph of f. Okay. So again, to recap some of the stuff that we've learned before, we know the end behavior of the graph depending on the degree and if the function is even or odd, the multiplicity of the zeros, now the true zeros, and also one thing that we can also look at is our y-intercept. Here, since it's in general form of this polynomial, the constant is always our y-intercept. We don't have to do math, but again, if you had to find the y-intercept, remember, you set x equal to 0. 0 cubed is 0, 0 squared is 0, 9 times 0 is 0, 0 minus 9 is just going to give me my -9, my constant term. So let's go ahead and put all of this together, okay? So again, just to review my end behavior, I am dealing with a degree 3 polynomial. So 3 is an odd number, so this is an odd function. The leading coefficient of this polynomial is a positive value 1. So what this means is the end behavior of this odd function is going to fall on the left, rise on the right. And that graph is represented here, yes? Um, so it's this one here, okay? Now, my zeros are at -3, -1, and 3, okay? They're all odd multiplicity. So what that means is that these three values actually cross the x-axis. There's none of them that touch and turn back. That only happens when we have double zeros or an even multiplicity, okay? So here, again, the -3 at x equals -3, it crosses at x -1, it crosses at x equals 3, it crosses the graph. Okay. Again, my y-intercept, which is what I explained already, got ahead of myself, is that y equals -9, or as an ordered pair, when x is 0, y is -9. And then we can pick additional points to make our graph a little pretty. Okay, so again, these are the zeros that I found, the -3, -1, the +3. Okay, I know the end behavior, it's going to fall on the left, rise on the right. Okay, this is where the additional points will help, and the points that I would pick are between my critical points. I would pick values between -3 and 1, in between maybe um, -1 and 0, and from 0 to 3. And if you see here, this is what I picked. These are the values. I picked 1, I picked 2, okay? And when I plugged these points in, this was just to give me a general idea of what this graph is going to look like. And this looks like my cubic function, yes? Now, again, that one was the ugly hand version, but again, in the computer, when you do WebAssign will do all the work for you and it will be nice and neat. Again, all you have to do is put those critical points and the computer will do the rest, okay? All right, so let's continue practicing a little bit more with these complex numbers. So it says, find a polynomial function with real coefficients that have the given zeros. Okay, so here they're giving me two zeros. They're giving me a zero, a real zero at 3, and they're giving me an imaginary zero or a complex zero, which is at -4i. Okay, now my goal is to you have the quotient, okay, equal the product of this. Yes, so my goal is to have this polynomial. So one way to do it is, again, grabbing the factors of these and multiply them together. So here the factor of 3 is x equals 3, so I know that the factor is going to be x minus 3, and then they gave me the -4i, but we know that since this is a complex number and it came from a square root, okay, this will always have its partner, the positive, okay? So please keep that in mind. Even though they gave me just one of them, I know the third one, or the second one in this case, which is the positive 4i. So to find the degree of this polynomial, I can get the factors of these three, okay, and I will multiply them together and it will give me my answer. Now, what I am doing here is what's called the linear factorization theorem. That says that when you multiply all of the factors together, you will end up with the polynomial. Now, there's only one thing that we need, the a value, and I'll show you how to get around that. So let's go ahead and solve this problem, okay? So again, these are my zeros. I'm going to get the factors of these zeros, which are, again, x minus 3, x plus 4i, and x minus 4i. And what I'm going to do is, again, I'm using what's called my linear factorization theorem. My linear factorization theorem says that if I multiply all the factors, I will get my polynomial. But the linear factorization theorem has my leading coefficient, okay? Now, my leading coefficient a sub n, right now, I don't know, but I will figure that out in a second, okay? So let's do the multiplication. Now, what I like to do first is I like to start from the far right and I move left, okay? So what I'm going to do is I'm going to multiply first my two complex numbers again, and this would be FOIL, okay? So the x times the x times minus 4i, then the 4i times the x, and then the 4i times the -4i, okay? So let's go ahead and do it. So when I do this, I have this. I can combine my like terms, okay? I have minus 4ix plus 4ix cancels, okay? And then I have an I squared, but we reviewed that I squared is equal to -1. So I'm going to replace the I squared with -1. So this is going to simplify with x squared plus 16, okay? Now I'm going to do one more multiplication. Now the x minus 3 to the x squared plus 16. So the x times the x squared, the x times the 16, the -3 times the x squared, and the -3 times the positive 16. And when I do that, okay, I have x cubed plus 16x minus 3x squared minus 48. Okay, there's no like terms that I can combine, so that is my answer. So the only thing that I'm missing here is to get the a sub n. Okay, so to do that, what I'm going to do is first I'm gonna put this in descending order. I'm gonna put it regularly. So I have x cubed minus 3x squared plus 16x minus 48. Okay, so here, okay, what I'm gonna do is I'm gonna tell you that this particular problem my leading coefficient is 1. Okay, but there's going to be a way for us to solve for this. When they don't give it to us, we can assume it's 1. But in this particular problem, we're going to do the same process, but they're going to give us all the tools to get that leading coefficient. So this problem states this. I want to find a polynomial that has a degree 4, has zeros at these values here, and I have a solution point. And again, this extra piece of information, the solution point, is going to allow me to get that leading coefficient. Okay, so let's go ahead and do it. So the first thing that I do is I grab my zeros. I have x equals negative 4, x equals 1, x equals I. But keep in mind, that the fact that they gave me an imaginary number always has its partner because it came from the square root. So this one will always have the negative I. So again, the factors are x plus 4, x minus 1, x minus I, x plus 1. I'm going to use my linear factorization theorem that says that when I multiply all these factors, I'm going to get back the original polynomial. So let's go ahead and do this. Again, I'm going to start with the farthest right. And when I do this, I have this, combine my like terms. I know that I squared is a negative 1. So this is going to give me x squared plus 1. Now let's do the next one, x minus 1 times the x squared plus 1. When I do that multiplication, I have x cubed plus x minus x squared minus 1. Nothing can be combined, so I don't have any like terms. So now just the last multiplication. The x plus 4 times this polynomial here, which is going to give me this long polynomial. Let's combine my like terms. Okay, so here I have a lonely x to the fourth. I have a minus x cubed and a positive 4x cubed. So minus x cubed plus 4x cubed is a minus positive 3x cubed. Okay, and now I have a positive x squared and a negative 4x squared, and then I have a negative x. So sorry, I'm missing a square here. So I have a positive x squared. Oh no, only and minus 4x squared is a minus 3x squared. And then I have a minus x plus 4x is a positive 3x, and I have the lonely constant, the negative 4. Okay, so if you see here, we have the same problem that we had before, but now we have an actual way of finding this leading coefficient. And I'm going to use again this information here, the solution point. And the solution point states this, that if I choose x to be 0, the output or the y value is going to be negative 8. So I'm going to do that. I'm going to replace this polynomial here. What this is saying is that when I plugged in 0 for x, the solution is negative 8. So now all I have to evaluate, okay? And when I evaluate here, 0, 0 to the fourth power is 0, 0 to the third is 0, 0 times 3 is 0, 0 squared is 0, 0 times 3 is 0, 3 times 0 is 0, and 0 minus 4 is minus 4. So I have negative 8 is equal to a sub n times negative 4. So to solve for a sub n, I'm going to divide both sides by a negative 4, and I'm going to see that a sub n is 2. So I'm going to replace that 2, that a sub n with a 2 over here, okay? And I have this. To get my answer, I'm going to distribute that to this polynomial. And I'll have 2x to the fourth plus 6x cubed minus 6x squared plus 6x minus 8. Again, with this information, I was able to come up with the question that they're asking me. Come up with the polynomial with these given characteristics. Again, my polynomial, if you see, is a degree 4. The highest exponent is a 4. The zeros are these. If I were to double check my work, if I plug in the negative 4, the 1 to this, I'm going to get a remainder of 0. And if I put 0 here, my answer would be negative 8. Okay. So again, this is a review of this section. So again, I thank you for joining me for today's session. Again, if you joined me right now, you're here with me, and you want a copy of the presentation on the top of your screen, all you have to do is click on the arrow with the little box pointing down. You can download that to your computer. Again, thank you so much. Enjoy your spring break. And now I'll pass it back to our presenters. Thank you so much.
Thank you, Mr. Carrizales, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on our YouTube playlist. Today's session will also be available on that playlist later on today. Also linked is a short survey to help us improve our TV sessions. Please take time to fill out the survey. Before you leave, I want to share the TV sessions for next time. I do want to remind you, like Mr. Carrizales said, that we will be on spring break. Please enjoy yourself. We'll be out from the 10th to the 14th, and there will be no Happy Math Hour for next week. We will be back on March 21st. Both 1314 and 1324 Math will be covering Exam 2 reviews. Thank you all for coming in today. We hope you have a lovely weekend and also a great spring break. Get some rest. But today, don't forget that at 1 p.m. we will also have student success topic. They will be covering the Pasos, Cesar Chavez, and the oral history. Again, have a great spring break, guys. Thank you for joining us.